Today, we will talk about the altimeter. The altimeter is one of the basic flight instruments, and it is connected to the pitot static system, which we discussed in a previous video. Here we have a simple schematic of a typical pitot static system. As we can see, the altimeter is connected only to the static port, which means that it receives static pressure information only. Now, before continuing, we should mention that there are different types of altimeters depending on their principle of operation. First of all, we have the barometric altimeter. This type of altimeter, as its name implies, uses barometric pressure to give its reading. Then we have the radio altimeter or radar altimeter, which uses radio waves to measure the height in relation to the surface. And finally, there's the GPS or GNSS altimeter, which uses satellite-derived geometrical data to determine the altitude. In this particular video, we will focus on the barometric altimeter, as it is the one used in most air operations and can be found in all aircraft. So let's see exactly what a barometric altimeter is. In simple terms, this is an instrument that measures the vertical distance between the aircraft and a specified reference level. This reference level will be the one at which the altimeter will indicate 0. And therefore, the altimeter will measure how high the aircraft is with respect to that level. This vertical distance can be expressed in terms of feet or meters, even though most altimeters are calibrated in feet. At this point we might be wondering, why do we say vertical distance instead of altitude or height? Well, that is because that vertical distance may have different names depending on the reference level we are using. Let's see an example of this. If we measure the vertical distance between the mean sea level and the aircraft in flight, we will be measuring altitude. If we measure the vertical distance between a point on the ground and the aircraft in flight, we will be measuring height. And if we measure the vertical distance between the mean sea level and a point on the ground, we will be measuring elevation. Now, the term flight level is also used to refer to a certain vertical distance, however we will deal with that concept later. So far, we will only be using these three concepts of altitude, height, and elevation. With this being said, let's now focus on how does a barometric altimeter actually work. As previously mentioned, this type of altimeter uses static pressure, or in other words, atmospheric pressure to determine altitude. It takes advantage of the fact that the static pressure decreases with altitude. Therefore, if we measure the pressure at low altitudes, it will be higher than the pressure at higher altitudes. This means that, if the altimeter senses a high static pressure, it will interpret that the aircraft is flying at a low altitude. And in the same way, if it senses a low static pressure, it will interpret that the aircraft is flying at a high altitude. So in other words, the barometric altimeter interprets pressure changes as altitude changes. That's the reason why the altimeter needs to be connected to the static port, since it needs to detect changes in atmospheric pressure to give the altitude reading. Now, by default, the altimeter is calibrated to measure the altitude in relation to the mean sea level under standard conditions. As we mentioned in the video about standard conditions ISA, the standard pressure at sea level is 2992 inches of mercury, or 1013 hectopascals. In this video, we will use inches of mercury in the examples, however the concept is the same for hectopascals. In this case, if the altimeter senses a static pressure of exactly 2992 inches of mercury, it will read 0 feet, since it is the barometric reference level. Now, if the aircraft starts to climb, the static pressure will decrease, and therefore the altimeter will show an increase in altitude. Let's suppose, for example, that this aircraft climbs up to a point where the static pressure is 2514 inches of mercury. In this case, what the altimeter does is compare the new static pressure value with the reference pressure of 2992 inches of mercury. And based on the resulting pressure difference, the altimeter can calculate the altitude above the reference level. Having understood this basic principle, let's see what actually happens inside the instrument case. As we know, the instrument is connected to the static port, which fills the instrument case with static pressure. Now, inside the instrument there's an aneroid capsule, which is sealed with a constant pressure inside of 2992 inches of mercury, which, as we previously mentioned, is the standard reference pressure. This capsule is connected to gears that move the needles on the instrument dial. In this case, if the aircraft is at sea level, the static pressure inside the case will be roughly equal to the pressure inside the aneroid capsule. In this situation, the aneroid capsule will be contracted and the needles will indicate 0 feet. Now, if the aircraft starts climbing, the static pressure inside the case will gradually reduce. And since the pressure inside the capsule remains the same, the pressure differential will cause the capsule to expand, moving the gears which in turn move the needles of the altimeter to indicate an increase in altitude. On the other hand, if the aircraft starts descending, the static pressure will gradually increase, causing the aneroid capsule to contract again, moving the gears and needles to indicate a lower altitude. So far, we have used 2992 as the reference pressure at sea level. This pressure is known as the barometric reference, which, as we previously said, is the pressure level at which the altimeter would indicate 0 feet. And all indications will refer to the altitude of the aircraft in relation to this level. By default, this barometric reference is 2992 inches of mercury, just because it's the standard sea level pressure. However, in practice, the pilot can actually change this barometric reference to any other value. But we might be wondering, why does the pilot need to change the barometric reference? Well, let's look at it by means of an example. As we already know, the actual altitude is the vertical distance between the mean sea level and the aircraft. And under standard conditions, the pressure level that identifies the mean sea level is 2992 inches of mercury. From this point, the static pressure decreases with altitude at a rate of approximately 1 inch per 1,000 feet. And theoretically, below the mean sea level, the static pressure would increase at the same rate. Each of these lines that identify a pressure level is called an isobar, and they will be very important for this explanation. Here, under standard conditions, as our altimeter is calibrated by default to use 2992 as barometric reference, it will indicate the vertical distance between the 2992 isobar and the aircraft. And as the 2992 isobar and the mean sea level are in the same position, the indicated altitude will be the same as the actual altitude. The thing is that, in reality, we almost never have standard pressure conditions, so in other words, the 2992 isobar almost never identify the mean sea level. Let's look at two different scenarios, one with a higher than standard pressure and the other with a lower than standard pressure. Let's begin with the higher than standard pressure case. Here, the isobars will move upwards, causing the 2992 isobar to no longer represent the mean sea level. Now, the new pressure level that identifies the mean sea level is the 3040 inches of mercury isobar. In this situation, if our altimeter is still adjusted to use 2992 as barometric reference, the indicated altitude will be lower than the actual altitude. This happens because the instrument is measuring the altitude in relation to the 2992 isobar, which in this case is higher than the mean sea level. The solution here is to readjust the altimeter to use 3040 as the new barometric reference, since it's the current pressure level that identifies the mean sea level. This way the altimeter will measure the actual altitude correctly. The current level pressure that identifies the mean sea level in a certain moment is known as QNH, and it will vary depending on the atmospheric pressure changes. It is therefore important that the pilot receives updated QNH information at regular intervals while flying in order to adjust the altimeter to indicate the actual altitude precisely. Let's have a look now to a lower than standard pressure condition. In this situation, the isobars will now move downwards, causing the 2992 isobar to no longer represent the mean sea level. In this case, the new pressure level that identifies the mean sea level is the 2970 isobar. In other words, the QNH is now 2970 inches of mercury. So if in this situation the altimeter is adjusted with 2992, the indicated altitude will be higher than the actual altitude. Therefore, in order to obtain a correct altitude reading, the pilot will have to adjust 2970 as the new barometric reference, since it's the new pressure level that identifies the mean sea level. So far, we have seen examples where we adjust the altimeter to get a correct altitude reading. But what if we want to measure the height in relation to the terrain instead of the altitude in relation to mean sea level? Well, in this case, the pilot can adjust the altimeter to use the ground level as reference. First, let's refresh some concepts. As we mentioned, the vertical distance between the mean sea level and a point on the ground is known as elevation. And under standard conditions, we would have the isobars distributed as follows. So how should the pilot adjust the altimeter to indicate the height above the airport? In this particular case, the airport elevation is 2,000 feet, and as we can see, the pressure level that identifies 2,000 feet is 2792. So in order to indicate height above that airport, the altimeter must be set to use 2792 as barometric reference. In this situation, as we are no longer using the sea level pressure as a reference, the value used to adjust the altimeter is no longer the QNH. It is now the pressure at the airport level, which is known as QFE. Now, as with the QNH, if the pressure conditions are different from the standard, the QFE for a certain airport will vary. Therefore, it is important to obtain updated QFE information if we want to use heights instead of altitudes in our altimeter. You might be wondering by now, how can the pilot adjust a certain barometric reference in the altimeter? Well, that is performed through the Colesman window. This is a little window in the instrument dial which allow the pilot to change the barometric reference using the knob labeled as Baro Adjust in the bottom left corner. The Colesman window is calibrated either in inches of mercury or hectopascals. There are even instruments that include both pressure scales. So to summarize, if we adjust the QNH as barometric reference, the altimeter will indicate the altitude above mean sea level. While if we adjust the QFE as barometric reference, the altimeter will indicate the height above the airport. It is therefore logical that if we adjust the QFE of the airport while on the ground, the altimeter should indicate 0 feet. Now that we have seen how the altimeter works, let's see how the needles of the instrument are interpreted. First of all, let's see which are the different needles we will find in the dial. There is the triangular needle, which indicates tens of thousands of feet. So if this needle points the number 1, it represents 10,000 feet. If it points number 2, it represents 20,000 feet and so on. Then, there is the short needle, which indicates thousands of feet. So if this needle points the number 1, it represents 1,000 feet. If it points number 2, it represents 2,000 feet, and so on. Finally, there is the long needle, which indicates hundreds of feet. So if this needle points number 1, it represents 100 feet. If it points number 2, it represents 200 feet and so on. Let's see some examples of how to read the altimeter using the 3 needles together. In this case, all 3 needles are pointing 0, which indicates 0 feet. So in other words, the aircraft is exactly at the barometric reference level. Now let's suppose the aircraft climbs and the altimeter shows this indication. In this case, the triangular needle is between 0 and 1, therefore it indicates that the aircraft is between 0 and 10,000 feet. Then, the short needle is between 1 and 2, which means that the aircraft is above 1,000 but below 2,000 feet. And finally, the long needle is pointing number 4, which represents 400 feet. So with this, the altimeter reading is 1,400 feet. In this other situation, the triangular needle is between 0 and 1, the short needle is between 7 and 8, and the long needle points number 5. So the altimeter reads 7,500 feet. And in this last situation, the triangular needle is between 1 and 2, which indicates an altitude above 10,000 but below 20,000 feet. The short needle points number 2, which indicates 2,000 feet. And the long needle points 0. This altimeter is then indicating 12,000 feet. Now, the use of this 3-needle system results in a little problem. If we observe these 2 altimeters, we can see that the short and long needles are in the same position. However, the altimeter on the left is indicating 2,000 feet, while the one on the right is indicating 12,000 feet. So the only way to notice the difference is by looking at the triangular needle, which sometimes can be difficult to see, especially under high workloads. So it is likely that an unaware pilot may misinterpret the reading. This is the reason why most altimeters incorporate a 10,000 feet flag with black and white stripes. This flag is visible when flying below 10,000 feet, but it disappears when flying above this altitude. This way the pilot can easily determine if the aircraft is flying above or below 10,000 feet. The other thing to take into account is that each altimeter has a certain maximum calibration altitude. Since some barometric altimeters are more sensitive and accurate than others, each altimeter is certified to measure the altitude correctly up to a certain level. In this particular example, we can read in the dial that this altimeter is calibrated up to 20,000 feet. So if the aircraft climbs above 20,000 feet, the altitude reading may have significant errors. This happens because as the pressure reduces with altitude, it is more difficult for the altimeter to sense correctly the changes in pressure and interpret them as changes in altitude. This is why some altimeter designs are more accurate than others. For example, there is the simple altimeter, which is widely used in small aircraft that fly at low altitudes. The sensitive altimeter incorporates a second aneroid capsule and a temperature compensation system, which increase the accuracy and performance at higher altitudes. And finally, the servo-assisted altimeter incorporates an electric motor that allows the instrument to measure the pressure changes with a much higher accuracy. Now, there are also different types of instrument presentations. Some altimeters replace two of its needles for a numeric altitude indication, as we can see in the picture. And some others are adapted and incorporated into digital presentations of the electronic flight instrument system. Now, we must bear in mind that the altimeters are not perfect. They present instrument errors related to wear of the gears and mechanical imperfections, as well as position errors caused by pressure measurement errors of the pitot static system due to maneuvers or changes in aircraft configuration. This is why the manufacturer publishes an altitude calibration table that allows the pilot to apply the corresponding altitude corrections in order to obtain the calibrated altitude. This table takes into account altitude, airspeed and aircraft configuration to show the corrected values. However, normally these are small corrections that do not exceed 50 feet. Now, as we can see, this altitude calibration table is designed to be used with the normal static source. But what happens if this static port gets blocked? Well, in this case, the altimeter reading will freeze. So, regardless of subsequent changes in altitude, the instrument needles will be frozen, indicating the altitude at which the static port got blocked. Let's see what actually happens inside the instrument in this situation. When the static port gets blocked, the static pressure inside the instrument case will be trapped, and therefore it will remain constant. This means that the aneroid capsule inside the instrument will not expand or contract, keeping the needles frozen. So, how can the pilot solve this situation? Well, in most aircraft there is an alternate static source, which can be activated from the cockpit using a switch. Now, in case of using this alternate source, the pilot must consult the corresponding altitude calibration table. Since, as we already know, the static pressure sensed by this alternate source is slightly different. Here we can see an example of an alternate static source altitude calibration table. As we can see, it is very similar to a regular altitude calibration table, so it is used the same way. We will talk about altimetry and altimeter setting procedures. These are a set of definitions and procedures used to ensure adequate vertical separation from terrain and other aircraft using barometric altimeters, which are the altimeters that we find on all aircraft. These procedures take into account daily changes in atmospheric pressure, terrain characteristics, air traffic flow and ATS services provided, as well as all applicable local or regional procedures. However, before going into detail on this topic, let's recall some of the definitions we have seen in previous videos. Let's start with the different ways we have to express the vertical position of an aircraft. In first place, if we measure the vertical distance between the mean sea level and an aircraft in flight, we will be measuring altitude. If we measure the vertical distance between a point on the ground and an aircraft in flight, we will be measuring height. And finally, if we measure the vertical distance between the mean sea level and a point on the ground, we will be measuring elevation. Now, the concept of flight level also refers to a certain vertical distance, however, we will deal with it later. We must also remember how a barometric altimeter works. This type of altimeter uses static air pressure to give its reading. It takes advantage of the fact that atmospheric pressure decreases with altitude. This means that at low altitudes there's a higher pressure, while at higher altitudes the pressure decreases gradually. So if the altimeter senses a high static pressure, it will be interpreted as a low altitude. And as the aircraft climbs and the static pressure decreases, the altimeter will interpret it as an altitude increase. In other words, an altimeter is a very sensitive barometer that interprets static pressure changes as altitude changes. Now, since this type of altimeter uses pressure to give its reading, there must be a certain pressure level at which the altimeter reads 0 feet. That pressure level is known as the barometric reference. As mentioned before, this is the pressure level at which the altimeter will indicate 0 feet. And therefore, it is also the level in relation to which the altitude will be measured. And as we said in the previous video about the altimeter, it is calibrated by default to use a barometric reference of 2992 inches of mercury or 1013 hectopascals. It is used as the default barometric reference since it is the standard pressure at sea level under ISA conditions. However, since in practice sea level pressure varies constantly, the pilot can adjust the altimeter to use another barometric reference through the Colesman window, causing the altimeter to measure the altitude in relation to the desired pressure level. With this being said, let's see an example. Suppose that under certain conditions the pressure at sea level is 2972 inches of mercury, so in other words this would be our QNH, since as we saw in the previous video, the QNH is the pressure level that identifies the mean sea level. This means that if the pilot adjusts the altimeter with 2972 as the barometric reference, it will measure the altitude in relation to mean sea level. On the other hand, let's suppose that this airport that is at a certain elevation above mean sea level has a pressure of 2792 inches of mercury. In this case, this would be the QFE, which is the pressure level that identifies the airport level. This means that if the pilot adjusts the altimeter with 2792 as the barometric reference, it will measure the height above the airport. Now, apart from these two settings, there is another one known as QNE, or standard setting, which always represents the pressure level of 2992 inches of mercury, or 1013 hectopascals, which in this particular case is below mean sea level. If the pilot adjusts the altimeter with the QNE, it will indicate the current flight level. With this in mind, let's see a little summary. There are three main barometric references that are used in altimetry. First, we have the QNH, which is the pressure level that identifies the mean sea level, and therefore the altimeter will indicate altitudes. Then we have the QFE, which is the pressure level that identifies a certain airport elevation, and therefore the altimeter will indicate heights. And finally there is the QNE, which identifies the standard pressure level of 2992 inches of mercury, or 1013 hectopascals, and therefore the altimeter will indicate flight levels. With this being said, let's look more in detail at the concept of flight level. The flight level is the vertical distance between the standard pressure level of 2992 inches of mercury, or 1013 hectopascals, and an aircraft in flight. In other words, the altimeter will indicate the current flight level, as long as the QNE is set as the barometric reference. Something important to mention is that flight levels are identified with the abbreviation FL, followed by 3 digits which represent hundreds of feet. Let's see an example. Suppose that with the QNE set as barometric reference, the altimeter indicates 3,000 feet. In this case this would be represented as flight level 030, abbreviated as FL030. In this order of ideas, if the altimeter reads 15,000 feet, it would represent flight level 150. If it indicates 26,500 feet, it would be flight level 265. If it indicates 30,000 feet, it would be flight level 300, and so on. Now, let's go through some practical examples of situations that may arise. Let's begin with standard conditions. In this case, the sea level pressure is 2992 inches of mercury, which means that QNH and QNE will be equal, and therefore the altitude and flight level will be the same. And using this setting, while on the ground, the altimeter will read elevation. Now, suppose that at this particular airport, the QFE is 2792 inches of mercury. If the pilot sets this as barometric reference, the altimeter will read the height of the aircraft above that airport. Let's now see what happens in a lower than standard pressure condition. This means that the sea level pressure is lower than 2992 inches of mercury. Let's suppose it is 2972 in this example. This would be then the QNH. If we adjust it as barometric reference, the altimeter will read the altitude of the aircraft in flight, or the airport elevation, if the aircraft is on the ground. In this situation, the QNE, or standard pressure level, will be below mean sea level. If we adjust it as barometric reference, the altimeter will indicate the flight level, which as we can see, is higher than the altitude. Finally, let's suppose that the QFE at this airport is 2762 inches of mercury. If it is set as barometric reference, the altimeter will indicate the height above that airport. On the other hand, if there is a higher than standard pressure condition, the sea level pressure will be higher than 2992 inches of mercury. Let's say it is 3042 inches of mercury, this would be then the QNH. If we adjust it in the altimeter, it will read the altitude, or elevation above sea level. In this case, the QNE, or standard pressure level, will be above sea level. If it is adjusted in the altimeter, it will read the flight level, which as we can see, is lower than the altitude. And finally, if the QFE is for example 2842, it will allow the altimeter to read height above the airport. Now, the vertical position of an aircraft in flight can be expressed in any of these terms, depending on the barometric reference used. So in order to avoid misunderstandings between aircraft and air traffic control, certain standard procedures have been established to know what barometric reference to use in a certain moment. In essence, these are the altimeter setting procedures. First of all, we must say that the main objectives of these procedures are to ensure an adequate vertical separation from terrain and other aircraft in flight. So let's first look at the separation between aircraft. In this case, in order to have an adequate separation between aircraft, it is required that both of them use the same barometric reference. Let's see an example. Suppose there are two aircraft flying in opposite directions. In this case, let's say the QNH of the area is 30.06 inches of mercury. So if both aircraft use 30.06 as their barometric reference, they will be measuring their altitude in relation to the same pressure level, and therefore they can ensure an adequate vertical separation. In this case, one of them is flying at 7,000 feet and the other at 8,000 feet, so the actual separation is 1,000 feet. Now, something important to note is that even if these aircraft are not using the QNH, as long as both of them use the same altimeter setting, the vertical separation will be ensured. For example, let's say that in this case both aircraft use QNE instead of the local QNH. Despite they are not measuring the correct altitude, both are using the same reference, therefore they will have the same vertical separation. In conclusion, regardless of the altimeter setting being used, as long as both aircraft use the same, the vertical separation will be ensured. Otherwise, if one of them is using a different altimeter setting, the apparent separation will be different from the actual separation, which is quite dangerous. Let's see this through an example. Suppose we have the same situation here, and the local QNH is 30.31 inches of mercury. The aircraft on the left is using the local QNH of 30.31, but the aircraft on the right is using QNE instead of QNH. Apparently, if both aircraft report their altitude, their separation would be 1,000 feet. However, since both altimeters are measuring the altitude in relation to different pressure levels, the actual separation is different. In this particular case, the aircraft using QNE would be flying at an actual altitude of 7,650 feet, despite the indication of its altimeter of 7,000 feet. Therefore, in this situation the actual separation is only 350 feet, which represents a risk of collision. Let's now move on to the other case, the separation with the terrain and obstacles. In order to ensure an adequate separation with terrain and obstacles, it is necessary to use the QNH, since it allows the pilot to know the real altitude above sea level. Actually, the QFE of a certain airport could also be used for this purpose. However, it is little used worldwide since it leads to confusion and mistakes under certain conditions. So, even though it is used in some countries, we will focus on the use of QNH. With this in mind, most charts and procedures show the elevation of terrain and obstacles in relation to sea level. For example here, the top of this mountain has an elevation of 2,000 feet above sea level. Therefore, a pilot who is planning to fly through this area with a separation of 1,000 feet would have to fly at an altitude of 3,000 feet using the local QNH, which in this case is 30.10 inches of mercury. If otherwise this aircraft uses an altimeter setting other than the QNH, the apparent separation with terrain will be different from the actual separation, which can be really dangerous. Let's look at this example. Here we have the same situation, but now the local QNH is 2970 and the altimeter of the aircraft is set with the QNE. Here, although the pilot is reading 3,000 feet on the altimeter, that is not the real altitude of the aircraft, since it is using a barometric reference which does not correspond to the sea level pressure. In this particular case, the actual separation with terrain is only 800 feet. In conclusion, while flying close to the terrain and obstacles, it is important to always use the updated QNH of the area in order to ensure an adequate terrain clearance. Now that we know the requirements that we need to comply with in order to have an adequate separation with other aircraft and terrain, let's evaluate two different cases. The first one is an aircraft flying at low altitudes. In this case, at low altitudes there will be obstacles and terrain, as well as other nearby aircraft flying. Now, as previously mentioned, in order to have an adequate separation with terrain, the altimeter must be set with the local QNH. And, in order to ensure an adequate separation with other aircraft, all of them must use the same altimeter setting. It is then logical that, to comply with both requirements, all aircraft operating at low altitudes must use the local QNH. This way, they will be separated from terrain, and as all of them are using the same QNH, they will also be separated from each other. With this being said, let's see what happens when flying at higher altitudes. In this case, there is no terrain or obstacles, so it is not longer a problem. There are only nearby aircraft flying around, so it is only necessary to ensure adequate vertical separation between aircraft. And to do so, the only requirement is that all of them use the same altimeter setting. The altimeter setting to be used at high altitudes does not necessarily have to be the QNH, since as we just said, the terrain is no longer a problem. So in order to establish a standard setting to be used at high altitudes, the only setting that remains constant regardless of the conditions is the QNE, since it is always 2992 inches of mercury or 1013 hectopascals. In other words, the setting to be used by all aircraft operating at high altitudes will be the QNE. And as all aircraft are using the same setting, the separation is assured. Now, having seen these two scenarios, we obtain something like this. At low altitudes, all aircraft must use QNH. However, the problem with this is that the QNH does not have a fixed value, it changes depending on the conditions of the different areas. So in this case, the pilot has to update the QNH setting on a regular basis, depending on the information provided by the ATC. On the other hand, aircraft operating at high altitudes will use QNE, which is always the same. 2992 inches of mercury or 1013 hectopascals. The question now would be where the change from QNH to QNE and vice versa should be made. Well, to answer that question, we have to introduce a few concepts. The first one is the transition altitude, abbreviated as TA. This is the altitude below which all aircraft must use the local QNH and therefore express their vertical position in terms of altitudes. Then, we have the transition level, abbreviated as TL or TRL. This is the level above which all aircraft must use QNE and therefore express their vertical position in terms of flight levels. Finally, we have the concept of transition layer, which is the airspace between the transition altitude and the transition level. Something important to note regarding this transition layer is that it is not allowed to fly leveled within this layer, the aircrafts operating here must be climbing or descending. Keeping this in mind, all aircraft climbing through the transition layer must change from QNH to QNE when crossing the transition altitude. Therefore, within the transition layer, these aircrafts must express their vertical position in terms of flight levels, since they are using now QNE. On the other hand, all aircraft descending through the transition layer must change from QNE to QNH when crossing the transition level. Therefore, within the transition layer, these aircrafts must express their vertical position in terms of altitudes, since they are using now QNH. You might be wondering by now, how do I know what is the transition altitude and transition level for a certain area? Well, depending on terrain elevations and as provided by the Civil Aviation Authority, a transition altitude and level will be published for a certain area or airport. These values can be found in the charts of each airport or in the aeronautical information publication of each country. For example, we can see in this chart for Cali, Colombia, that the transition altitude is 18,000 feet and the transition level is flight level 190. In other words, in this case below 18,000 feet, all aircraft must use local QNH, while above flight level 190, all aircraft must use QNE. Here, the transition layer is between 18,000 feet and flight level 190. Now, in some cases, the transition altitude may have a fixed value, but the transition level is established by the ATC. In these cases, the air traffic control calculates the appropriate transition level to be used based on the current QNH and the published transition altitude. This transition level is reported through the IDIS or a communications VHF frequency. Now, another important procedure is that, in areas where a transition altitude or level is not published, or when there is no QNH information, all aircraft must use the QNE and express the vertical position in terms of flight levels. In this example, this aircraft departed using the local QNH from an area where the published transition altitude is 10,000 feet. But then, it enters an area where there is not a published transition altitude or level. In this case, the pilot must set the QNE and use flight levels until entering an area with a published transition altitude and where QNH information is provided. Usually this occurs in uncontrolled airspace in remote areas where there is no QNH information, such as, for example, jungles, deserts, oceans, etc. In these cases, the pilot must exercise extra caution since there's no way to assure an adequate terrain and obstacle clearance while using QNE. This is especially important when flying from high-pressure areas to low-pressure areas. In this case, the isobars will be inclined like this. On the left side, we can see that in the point A, the QNH is 30-40 inches of mercury. Then in the point B, it dropped to 30-00. And in this point C we can see that the QNH is now 29-60. Under these conditions, an aircraft flying from point A to point C would depart with a QNH setting of 30-40. However, if the pilot does not update the QNH in a long time while flying to the low-pressure area, the aircraft will be gradually descending. This happens because the aircraft is no longer using the correct QNH, which can lead to reduced terrain separation or even a crash. This situation is colloquially expressed in the phrase, "From high to low, look out below." However, not only pressure changes affect the altimeter reading, but also temperature changes. Let's see how does the air temperature affect the altitude indication. Here we have a column of air under standard conditions. If the temperature is colder than standard, for example in ISO -20 conditions, the isobars will be closer together. While if the temperature is warmer than standard, for example in ISO +20, the isobars will be further apart. This means, in other words, that air temperature affects the rate at which the pressure reduces with altitude, and therefore it will affect the reading of barometric altimeters. What this implies is that if we are flying, for example, at 7,000 feet under standard conditions and the temperature reduces, the true altitude will be lower than 7,000 feet. While if the temperature increases, the true altitude will be higher than 7,000 feet. This happens precisely because of the change in the spacing of the isobars with the temperature. According to the ICAO document 8168, the true altitude changes by 4% per each 10 degrees of ISO deviation. This rule of thumb is useful down to -15 degrees Celsius. With colder temperatures, it is necessary to consult the following table published in the document. Now, the effect of temperature leads to a situation quite similar to the one we saw with the pressure. In this case, if an aircraft is flying from a warmer area to a colder area, the isobars will be arranged in this way. As we can see, in the warmer area, the isobars are farther apart, while in the colder area they are closer together. This means that, even if the QNH remains constant, an aircraft flying to a colder area will gradually descend. This can lead to a reduced terrain and obstacle clearance, or even a crash. This is colloquially expressed in the phrase, "From hot to cold, look out below." Apart from these measurement errors of the altimeter with pressure and temperature changes, there's another one to take into account. It occurs in mountainous areas when the wind blows at high speeds. This produces local static pressure fluctuations due to the Bernoulli effect. This means that an aircraft flying in these areas may present erroneous altitude indications, and therefore it is necessary to increase the altitude safety margin with respect to the terrain. Having seen all these, let's move on to the altimeter error tolerance. The thing is that barometric altimeters may have an acceptable margin of error, which should be checked before each flight. The exact values are published on the ICAO document 8168. However, most manufacturers and operators consider that an adequate margin is plus or minus 75 feet. This means that if, for example, an aircraft is on the ground at an airport with an elevation of 3,000 feet, when adjusting the current QNH, the altimeter should read between 2,925 feet and 3,075 feet to be considered suitable for air operations. Otherwise, the altimeter must be checked and recalibrated by a certified aeronautical workshop. We will talk about the concepts of pressure altitude and density altitude, which are concepts widely used in aviation, especially in aircraft performance calculations. And if they are not well understood, can be quite confusing. So, without further ado, let's start with the pressure altitude. It is abbreviated as PA and corresponds to the altitude of the aircraft in relation to the standard isobar of 2992 inches of mercury or 1013 hectopascals, which, as we recall from previous videos, corresponds to the pressure at sea level under standard conditions. Therefore, we can also say that this pressure altitude is the altitude indicated by an altimeter adjusted with the QNE, since in this case, the altimeter would be measuring the altitude in relation to the standard isobar. And considering that in the ISA model, the pressure at each level has a fixed value, we can also say that the pressure altitude is the altitude in the ISA atmosphere where a certain pressure is found. Another thing to keep in mind is that the definition of pressure altitude is exactly the same as the definition of flight level. Therefore, the pressure altitude will always be equal to the corresponding flight level. Let's look at some examples of how this pressure altitude varies depending on the present conditions. Let's begin with the standard conditions. In this case, the sea level pressure is 2992 inches of mercury. Therefore, as the QNH and QNE are equal, we can say that the pressure altitude is equal to the actual altitude. Now, this only happens if the conditions are standard. Since if we have, for example, a higher than standard pressure conditions, the QNH will be higher than the QNE, which means that the 2992 isobar would be above the sea level. Therefore, in this case, the pressure altitude will be lower than the actual altitude. On the other hand, if there are lower than standard pressure conditions, the QNH will be lower than the QNE, which means that the 2992 isobar would be below the sea level. Therefore, the pressure altitude will be higher than the actual altitude, as we can see in this example. Having understood the concept of pressure altitude, let's see how it is calculated. There are several methods to do it. We can use either a table with correction values depending on the QNH, or directly use the altimeter of the aircraft, or use an approximate formula to determine the pressure altitude. Here are some examples of how to use each of these methods to determine pressure altitude. Let's begin with the table. Suppose we have the following conditions: a QNH of 3020 and an indicated altitude of 12,000 feet. Here, if we look at the table, we can see the different correction values to be applied depending on the QNH. In this case, for 3020 the correction value is -257. Therefore, all we have to do is take 12,000 feet and subtract 257 feet, obtaining a pressure altitude of 11,743 feet. Now, let's see how to determine the pressure altitude using the altimeter of the aircraft, using the same conditions as in the previous example. So, normally our altimeter will be adjusted with the local QNH of 3020, in this case indicating an altitude of 12,000 feet. To determine the pressure altitude, all we have to do is adjust 2992 in the altimeter and read the altitude indication. In this case 11,740 feet. Finally, let's see how to use the approximate formula using the same conditions. Here, we just have to replace the indicated altitude and the QNH in the formula and do the math. Obtaining a pressure altitude of 11,720 feet. It is important to mention that this formula is applicable only when using inches of mercury. If the QNH is expressed in hectopascals, we can use this other modified formula. Having seen what is the pressure altitude and how to calculate it, let's continue with the concept of density altitude, which is abbreviated as dA. It is defined as an altitude in the ISA atmosphere where a given density is found. It is a fairly short definition, however, sometimes it can be difficult to understand. So we will try to explain it in an easy and simple way through the following examples. First of all, we must part from the idea that in the Earth's atmosphere, the air density decreases with altitude due to the pressure reduction. This means that at low altitudes, the air molecules are closer together, which implies a higher air density. While at higher altitudes they are further apart, which implies a lower air density. It is important to note that air density is a determining factor in aircraft performance, since the thrust produced by the engines, the lift produced by the wings, among other things depend on air density. Therefore, it is very important to understand the concept of density altitude. Now, as we can see in the definition of density altitude, the ISA atmosphere is mentioned, since this is the main frame of reference to be used. Here we have then an air column with standard conditions. This means that at sea level we have a pressure of 2992 inches of mercury and a temperature of 15 degrees Celsius. And as we saw in the video about the ISA atmosphere, pressure decreases at a rate of 1 inch per 1,000 feet, while temperature decreases at a rate of 2 degrees Celsius per 1,000 feet. Therefore, at 1,000 feet we would have a pressure of 2892 and a temperature of 13 degrees. At 2,000 we would have 2792 and 11 degrees, and so on. Now, let us remember that air density depends mainly on pressure and temperature, although it also depends on humidity, but we will not take this into account. So, considering that in the ISA atmosphere the pressure and temperature at a certain altitude are always the same, this means that the density at a certain altitude will also be always the same. To illustrate this, let's assign a certain density value to each altitude in the ISA atmosphere, depending on the pressure and temperature at that altitude. We must clarify that these will be fictitious density values, which do not obey to any unit of measurement, since they will only be assigned for the purposes of the example. So, suppose that the combination of 2992 inches and 15 degrees results in a density of 12. Again, this is a fictitious value. Then, let's say that at 1,000 feet, the combination of 2892 and 13 degrees results in a density of 10. Then at 2,000 feet, a density of 8. At 3,000 a density of 6. And at 4,000 a density of 4. With this in mind, let's say we are at an airport with an elevation of 2,000 feet and the conditions are standard. Well, as we can see in the ISA model, at 2,000 feet we find an air density of 8. Therefore we say that the density altitude is 2,000 feet. Nothing complicated so far. We can then say that in standard conditions, the density altitude will be equal to the actual altitude. Now let's see what happens if the conditions at the airport change and we now have a higher than standard temperature and a lower than standard pressure. Well, the combination of these two factors will cause the air density to be reduced. Let's say, for example, that this combination of factors results in a density of 6. If we then look for this density value in the ISA model, we can see that we find it at 3,000 feet. Therefore we say that under these conditions, the airport has a density altitude of 3,000 feet. Although the actual elevation is 2,000 feet. This implies that the aircraft performance will behave as if the aircraft were flying at 3,000 feet, even though the actual elevation is 2,000 feet. Simply due to the fact that the conditions cause the air density to be lower. Now, the opposite happens when we have higher than standard pressure and lower than standard temperature conditions. In this case, the combination of these factors will cause the air density to increase. Suppose, for example, that the combination of these factors results in a density of 10. If we then look for this density value in the ISA model, we will find it at 1,000 feet. Therefore, we say that this airport under these conditions has a density altitude of 1,000 feet, although its actual elevation is 2,000 feet. This means that the performance of an aircraft will behave as if it were flying at 1,000 feet due to the increased air density. In conclusion, if the density altitude is low, it means that the air density is high. And if the density altitude is high, it means that the air density is low. For example, a density altitude of 1,000 feet will represent a higher density than a density altitude of 8,000 feet. Let's finish this explanation with the next example. Suppose that the airport A, with an elevation of 3,000 feet, reports a QNH of 38 inches of mercury and a temperature of 0 degrees Celsius. This indicates a relatively high pressure and low temperature, which will cause the air density to be high. Now, since the air density is high, it means the density altitude will be low. In this particular case, it is 1,670 feet. In other words, aircrafts operating at this airport will behave as if they were flying at 1,670 feet, which means that they will present a good performance. On the other hand, let's look at airport B, which also has an elevation of 3,000 feet. However, it reports a QNH of 2980 inches of mercury and a temperature of 30 degrees Celsius. This represents a relatively low pressure and high temperature, which results in a low air density. Now, since the density is low, it means that the density altitude will be high. In this particular case, it is 5,600 feet. In other words, aircraft operating at this airport will behave as if they were flying at 5,600 feet. Which means that they will present a poor performance due to the reduced air density. Now, having understood the concept of density altitude, let's see how to calculate it. There are several methods to do it. We can use a flight computer, either manual or electronic. We can also use a graph or table like this. Or we can use an approximate formula. It is important to mention that in some airports, the ITIS calculate and broadcast the density altitude based on the current conditions. That way, the pilot doesn't need to calculate it manually. With this being said, let's see some examples of how to determine the density altitude using each of these methods. Let's begin with the flight computer. For this, we will use the inner scales, specifically the little scale in the center and the upper right scale. In order to calculate the density altitude, we have to know in advance the air temperature and the pressure altitude. The first step is to align the pressure altitude with the corresponding air temperature in the upper right scale. Then we just have to read the resulting density altitude in the center scale. Let's look at a practical example. Suppose we have to determine the density altitude if the pressure altitude is 5,000 feet and the air temperature is -10 degrees. First, we have to align 5,000 feet with -10 degrees in the upper right scale, as we can see here. Once this is done, we read 3.1 in the center scale, which corresponds to a density altitude of 3,100 feet. Let's now move on to the approximate formula. To use it, it is required to know in advance the pressure altitude, the current air temperature, and the standard temperature at that altitude. This means that here we have an additional step, since we have to determine the standard temperature at the corresponding pressure altitude, which, as we will remember from previous videos, can be done by means of this other formula. Let's see a practical example. Suppose we have the same conditions as in the previous example. The first step then is to calculate the standard temperature at 5,000 feet. So we apply the corresponding formula, obtaining a temperature of 5 degrees Celsius. Once we have this information, we can now replace the values in the density altitude formula, obtaining as a result a density altitude of 3,200 feet. Finally, let's see this example using the graph. Here, the first step is to identify the line that represents 5,000 feet of pressure altitude, which is this one highlighted in yellow. Then, in the lower part, we look for the current air temperature, which is -10 degrees. And we draw a vertical line until intercepting the 5,000 feet line. Finally, we just have to draw a horizontal line to the left and read the resulting density altitude, which in this case is 3,150 feet approximately. We will talk about the types of altitude. In aviation, there are different concepts of altitude depending on their characteristics and practical applications. Here, we can mention the pressure and density altitude, which we discussed in a previous video. But we also have the indicated, calibrated, and true altitude, which we will see in detail in this video. So, let's begin with the indicated altitude. This is defined as the altitude indicated by an altimeter when adjusted with the current QNH. We can also say that this is the altitude corrected for pressure error. In other words, when the current QNH is adjusted, the reading is automatically corrected for pressure, thus obtaining the indicated altitude. This pressure correction is necessary since the pressure at sea level is not always the same, meaning that we need to change the barometric reference in order to obtain the correct altitude indication. Now, the thing is that, by default, the altimeter is calibrated to measure the correct altitude above sea level under standard conditions. And as we already know, under standard conditions, the pressure at sea level is 2992 inches of mercury, or 1013 hectopascals. So, this means that under standard conditions, with the default altimeter setting, the indicated altitude and the actual altitude will be the same, and therefore, a correction for pressure is not required. However, if there are higher than standard pressure conditions, the isobars will move upwards, and therefore, the pressure at sea level will be higher than 2992. In this particular example, it is 3040. In this situation, if our altimeter is still adjusted with the default setting of 2992, the indicated altitude will be lower than the actual altitude. So, in order to obtain the correct altitude reading, the altimeter must be adjusted with the current QNH, in this case, 3040. Now, on the other hand, the opposite happens if there are lower than standard pressure conditions. In this case, the isobars will move downwards, and therefore the pressure at sea level will be lower than 2992, in this case it is 2970. So, if our altimeter is still adjusted with the default setting, the indicated altitude will be higher than the actual altitude. So in order to obtain the correct altitude reading, we will have to adjust the current QNH of 2970 as the new barometric reference. With this then, it is clear that the indicated altitude is obtained when the current QNH is adjusted on the altimeter. However, the problem is that the altimeters are not perfect, they suffer from instrument error, which is caused by wear of the gears and mechanical imperfections. And there's also the position error, which is caused by pitot static system errors in pressure measurement due to maneuvers or changes in aircraft configuration, which we have already discussed in detail in the video about the pitot static system. As a result of these errors, we have the following concept of altitude, which is the calibrated altitude. This is defined as the indicated altitude corrected for position and instrument errors. However, usually these errors tend to be small, and therefore in practice it is normally assumed that the indicated altitude and calibrated altitude are roughly equal. Now, you might be wondering, how do we apply the corrections for instrument and position errors to obtain the calibrated altitude? Well, the manufacturer publishes an altitude calibration table in the aircraft manual, which specifies the corrections to be applied in order to obtain the calibrated altitude. In this table, altitude, airspeed and aircraft configuration are taken into account to determine the correction values, as we can see. So far, we have seen how the instrument and position errors affect the altitude reading. But there's another factor which also affects barometric altimeters, it is the temperature. This brings us to the concept of true altitude. As its name suggests, it is the actual altitude in relation to mean sea level. And in theory, it is obtained correcting the calibrated altitude for temperature error. And as we just said, the altitude reading is affected by the temperature of the air. For example, if an aircraft is flying under standard temperature conditions with the current QNH of 3010 adjusted on the altimeter, it will indicate the true altitude. However, if the temperature is lower than standard, even using the correct QNH, the true altitude will be lower than the indicated altitude. Otherwise, if the temperature is higher than standard, the true altitude will be higher than the indicated altitude. This error occurs due to the pressure distribution with altitude at different temperatures. For example, here we have the typical distribution of isobars under standard temperature conditions. Now, when the temperature is lower than standard, the pressure changes more rapidly with altitude, and therefore the isobars will be less spaced. On the other hand, when the temperature is higher than standard, the pressure changes slowly with altitude, and therefore the isobars will be further apart. And as we can see, the pressure at sea level is the same on all three cases, which means that the QNH is the same, the only thing that changes is the pressure distribution with altitude. This implies that under standard temperature conditions, the indicated altitude and true altitude will be the same, so a temperature correction is not required. But for example, if we are in high temperature conditions, the isobars will be further apart, and as we can see in this case, the true altitude is higher than the indicated altitude. The opposite happens if the temperature is low. In this case, the isobars will be closer together, and therefore, the true altitude will be lower than the indicated altitude. Now, in practice we may find a situation like this. Here we can appreciate the gradual change in the spacing of the isobars depending on the temperature. Note that the pressure at sea level remains constant, so the QNH is the same in both areas. This means that, if an aircraft flies from a high temperature area to a low temperature area, even though it uses the correct QNH, it will gradually descend, which could constitute a risk of collision with terrain. And conversely, if an aircraft flies from a low temperature area to a high temperature area, it will gradually climb, despite its altimeter will be indicating a constant altitude. Now that we have understood the effect of temperature and the concept of true altitude, let's see how it is determined. There are several methods to calculate the true altitude. We can use a flight computer, either manual or electronic. Or we can use an approximate formula. Let's see a couple of examples of how to use these methods. Let's begin with the flight computer. To use it, it is required to know in advance the indicated or calibrated altitude and the current temperature at that altitude. Then, the first step is to align the altitude with the corresponding temperature. And then, read the corresponding true altitude in the outer scale. Let's see a practical example. Suppose we want to determine the true altitude if flying at an indicated altitude of 16,000 feet with a temperature of 0 degrees Celsius. Well, first we have to align the altitude of 16,000 feet with 0 degrees Celsius on this scale. Then, we look for 16,000 feet in the middle scale and read the corresponding true altitude on the outer scale, in this case 17,000 feet. This means that, even though the altimeter is indicating 16,000 feet with the current QNH properly set, The aircraft is actually flying at 17,000 feet due to the relatively high temperature. Let's now see how to use the formula. To use it, it is required to know in advance the ISA deviation, since this is the formula we are going to use. As we know from the video about ISA conditions, the ISA deviation can be determined calculating first the standard temperature at that altitude using this formula, and then determining the difference in relation to the actual temperature. Let's look at the same example, but using this formula. Well, the first step is to calculate the standard temperature at 16,000 feet, so we just have to replace the altitude in this formula and do the math, obtaining as a result minus 17 degrees Celsius. This would be the standard temperature at 16,000, however the actual temperature is 0 degrees. So if we find the difference between the standard and the actual temperature using this other formula, we obtain an ISA deviation of plus 17. With this information, we can now apply the formula for the true altitude. We just replace the terms, do the math, and we obtain a true altitude of 17,088 feet. Now, having seen the theory regarding these types of altitude, let's see their practical applications. Under normal conditions, only pressure correction is applied. This means that the only thing that is done is adjust the QNH on the altimeter. Therefore, temperature correction is not usually applied. So the altitude used in most operations is the indicated altitude rather than the true altitude. However, if the temperature turns out to be well below standard, a safety factor must be added to the minimum flight altitudes to ensure adequate separation from terrain and obstacles. The correction factors to be used are published on the ICAO document 8168 and are provided by means of this table. These values are established based on an aerodrome at sea level, but they can be used for other elevations. Let's see a little example of how to use this table. Suppose that the minimum descent altitude, or MDA, of a particular instrument approach procedure is 400 feet and the temperature is minus 40 degrees Celsius. Using the table, we can see that the correction to be added to the MDA is 100 feet, obtaining a corrected minimum descent altitude of 500 feet. But you might be wondering, when is it required to apply this temperature correction? Well, most airlines establish specific policies as to when temperature correction should be applied. However, in some cases, like in the approach procedures with vertical guidance that use uncompensated Baro VNAV systems, an operational temperature range is specified in the chart. For example here, the second note establishes that this procedure may be executed without temperature correction, provided the temperature is between 16 and 40 degrees Celsius. If the current temperature is outside this range, the crew must apply the corresponding temperature corrections to all the altitudes of the procedure. On the other hand, the Civil Aviation Authority of each state usually takes into account the effective temperature when establishing minimum flight altitudes so that the pilot does not have to manually calculate the correction. Here we can see an example of this. This is a radar minimum altitudes chart for Innsbruck in Austria. As we can see, it says that ATC will apply the cold temperature corrections when necessary, and therefore the pilots doesn't have to worry about it. Normally this is done by making a survey of the average temperatures in the area, and based on this, the most conservative safety margins are applied. In summary then, if we adjust the current QNH on the altimeter, we will obtain the indicated altitude. If we then apply the instrument and position error corrections, we obtain the calibrated altitude. And if we then apply the temperature correction, we obtain the true altitude. However, as we already said, in practice the indicated altitude is the most commonly used, so the pilot only needs to worry about updating the QNH on a regular basis while flying. I hope the information presented in this video was useful. If so, don't forget to share, like, subscribe, and leave a comment down below. Thanks for watching.